Welcome back to day 3 of machine learning workshop. And let's start with opening the materials. As always, this is on GitHub, and here's a link to open the notebook with Jupyter Lab. Yesterday, we talked about classification models and how to fit hyperparameters using cross-validation. Today, we will talk about another class of supervised learning, which is regression, and some topics in unsupervised learning will be covered later. And then we will go to conclusions, and there will also be exercises for today. So is everybody ready with your notebook? Can you show me some type of reaction? All right, let's go ahead. Just like previous day, we will start with loading NumPy as NP and matplotlib.pyplot as PLT. And let's set this option to increase the font size within a plot. And let's go to regression. The task of regression is from a set of features to determine a continuous target, such as creating a function that estimates the cell volume from length, width, and smoothness of cell as features. So large V is a volume of a cell, and length is represented by L, width with D, and smoothness S. We are finding the values of alpha, beta, gamma, and intercept V naught to estimate the cell volume. And specifically, doing this is called linear regression. So linear regression is any regression model that is linear on the fitting parameters. Let's create a simple dataset from NumPy's random function. We will generate 100 samples with one feature, and the coefficient will be 0.5 with the y-intercept of 2.2. We will put random data of 100 and multiply it by 10 to make it fall between 0 and 10. And then as a form of noise, because data will always have some kind of noise in it, we generate random numbers from 0 and 1 and subtract 0.5 to make it the values between minus 0.5 and 0.5. So the maximum value in X and minimum value in X will be close to 0 and 10 respectively. In this case, 0.1 and 9.7. And the average of the error component is supposed to be close to 0, and in this case, it is 0.04. And we will define the dependent variable y, which will be our target, like this. So this is the exact model, 0.5 times x plus intercept of 2.2 plus some error. We will draw a scatter plot of it. On the x-axis, we will put this x, and on the y-axis, we will put the target y. And each will be represented by a circular marker. And let's use this color. This color code is for red, green, and blue respectively, with length 3 tuple. And we'll put x label feature, y label target, and show it. This is the data we generated. So with this data, what we are going to do is train a linear model with this particular formulation. And if everything works out, we should expect that the learned beta to be close to 0.5 and learned gamma to be close to 2.2. And before doing that, we will hold out some of the data as test set, which is customary in many machine learning tasks. We use train test split function as we did yesterday. Oh, by the way, the features are expected to be a matrix, so we reshape it as num samples by 1 matrix. And scikit-learn, of course, has a model for linear regression in a form of class, and that is named linear regression, of course. Here's a link to its documentation. We can load it with this command. The linear regression class is inside the sub-package linear model of scikit-learn. So we load the function, load the class like this, and we initialize the model and fit the model like this. Then we have learned the borrow from the training data. Now what we are going to do is just make some grid point and make predictions on them. So we will linear space 0 to 10 with 100 pieces, and make prediction. And by plotting it like this in second line, we will see a line that is representing our linear model. This is the line. So it looks like we have fit an okay model from our training data. Similar to the classifier we talked about yesterday, you can also access information on the fitted linear regression model through their attributes. The linear model has these attributes, and one of them is quiff underscore, where attributes ending with underscore, meaning that they are available only after fitting a model. This is the estimated coefficients for linear regression model. And intercept is an independent term in the linear model, and this is a value when x is 0. So if we print them out, for coefficient we have length 1 vector with a coefficient of 0.489, which is pretty similar to 0.5, which is the model we generated data from. And it looks also close to 2.2, which is also the model we generated data from. So visually, it looks okay. So what is the objective way to measure the performance? How to get some value to measure performance? In regression, similar to accuracy we use for classifiers, we have a most commonly used metric to evaluate the performance of linear regression in the concept named coefficient of determination. Its value is between 0 to 1. 1 is for the best fit and 0 for almost uncorrelated fit. And it can be negative if the direction is different. So it is defined as 1 minus u divided by v, where u is the residual sum of squares, which means that the true value minus the predicted value squared, and they sum together. And v is the total sum of squares, which means true values and their mean subtracted from it, and they're squared, and then we took sum of it. So the v represent total variation in the data, or total sum of squares. As you might see, there is nothing to do with our model. This is specific to the data set. And out of these total variation, how much is explained by our model is represented by the total sum of squares subtracted by this residual sum of squares. So its value will be between, so its maximum value will be 1. So the closer to 1 we get, we have a better model. And in this case, the I-square value is 0.9656, which seems pretty good. What we do next is polynomial regression. A linear regression is any regression of a model that is linear in terms of the fitting parameters. So if you have two features and the model is y equals beta 1x plus beta 2z plus gamma, it is a linear model. And how about this? Y equals beta 1x plus beta 2x squared plus gamma. although it is quadratic in terms of x, this is still considered a linear regression and can be solved using the same methods because this is just using two features of x and x squared. So let's create a 2D feature space with x and x squared in Python. The code to generate our data will be something like this: 0.5 times x plus 0.15 times x squared plus intersect plus error term we generated earlier. And here we go. What was going on here was that shape of this thing was 100 by 100. Oh, so yeah, I missed the point a little bit, I think. Let's get back to it. So we will regenerate the data. So what happens here is we get 100 times 100 data. And the reason for that, sorry. Okay, x is reshaped to 100 by 1. So if we run the cells sequentially up to this point, the shape of x is 100 by 1, and E is a length 100 vector. So if we just do this to generate the data, what we have is 100 by 100 matrix. And the reason for that is we have x as a 100 by 1 matrix and E as a length 100 vector at this point. And in that case, the vector E is treated as a row vector. So this results in 100 by 100 matrix. So what we have to do is reshape it as 100 by 1 vector to make it same shape as the vector x, as the 100 by 1 matrix x. And then we will have length 100 vector. Let's see the shape. It is 100 by 1 now. Let's plot x and y again. And then we have a data generated from this quadratic function. And once again, we will split the data into training and test sets and create a new feature matrix. So what we do here is create a matrix of zeros of size, number of samples, which is 100 by 2. And then fill the column 1 with the values in X train to make feature 0 as X data as it is, and fill column 1 of features matrix with the squared values of the data in X train to make feature 1 as a squared values of the training data. And what we do again is initializing a linear regression model and fitting the model. Then we will have length 2 coefficients and a intercept value. Coefficients, we have 2 values. First one is for the linear term 0.489 close to 0.5. And the second one is for the quadratic term, of course, and 0.151 close to 0.15 from which the data was generated from. And intercept is similar to 0.2. Intercept is similar to 2.2 as we expected. You can again calculate the prediction along the y-axis and plot it just like we did before. So x-array will be this again, and y-array will be based on the coefficient we learned from the model. So this is for the linear term, and this will be for the quadratic term, and we add intercept to it. And we draw a scatter plot for the data we had, and we will plot the line to get the fitted model, and the result looks like this. Looks adequate based on this figure, right? So this was a polynomial regression example. Is there any question so far? Okay, let's move on to the next item. Up next is regularization and overfitting. Let's explore a little bit more interesting data set. We have a regression exercise data set in the materials distributed. The file name is regression exercise dataset.dat. And we have 2 columns of it. We have 50 rows and 2 columns, and we will treat the first column, column 0, as target, and second column, column ID 1, as the feature for this regression. And we will split this data into training and test data set with the function train test split. We will shuffle the data, and we put test size as 0.2. So 20% of the data set will be held out as test data. And let's visualize the training data set. And it looks like this. And let's try to fit a linear model with this. And let's store in these arrays the average value of the coefficients, by the way. So we will create a empty list with a linear regression model, and we get an error. Why is that? Can anybody put it on the chat? Yes, we didn't reshape yet, and the array is in the wrong shape. And Aditya. So, inspecting the error message we get, let's read it a little bit. And what it says it's expected 2D array, got 1D array instead. So we had to reshape it into a matrix or 2D array. So the shape we had for X is 40 with length 1 tuple. So we reshape it like this to get a two-dimensional array. And then let's fit linear regression model again. And then let's put into the list we created up here. Let's put degree 1 because it is a linear model and it is 1 degree, and average of coefficients into coefs here. And we will visualize the fitted model with this X array and their predicted values. And we get this. This does not fit our data well. This is considered underfitting because the model we are trying to use is too simple. So to use polynomials with higher degrees, we need an array that serves as our input features, having as many columns as degrees in our polynomial. And using the C underscore trick provided in NumPy, it is now easy to concatenate two columns. So just this command will concatenate X and X squared into a 2-column matrix. So the X poly variable here is 40 by 2. And all we need to do is train on the features and plot it. So we initialize the model, fit the model, and because it is 2-degree polynomial, we put 2. We append 2 to our list of degrees, and mean of the coefficients to coefs list. And then we get predicted values for these gridded values of X, and we create an array of the features of the X array values itself and its squared value. And we plot it, and we get this curve. This still seems a little bit too simple for the data set we have. So let's create a function that create a 2D array of features for any degree. Here's what we are going to do. We are creating a getPoly function. The two arguments will be my array and degree for number of degrees. So we create the result matrix like this. my array that shapes 0, which is number of samples, by degree. And for each degree, for column J, we make the my array matrix input back to a one-dimensional vector using the method label. We discussed about this method yesterday, and we put the power of it up to j plus 1. Why j plus 1? Because j begins with 0, and we want to start with 1. So let's try with fifth degree polynomial. Adding terms by hand is not very efficient, but we can construct exponential array with an arbitrary polynomial by using this code. So we have 40 by 5 matrix now, each column representing each power of data to the each power of what we did. So for fifth degree polynomial, we do this to get the feature matrix, and we do this to get the features to predict on. So we create model, fit the model, and append the degree, and append mean of the coefficients. While array will be the predicted values, and we visualize it in a red line. And it looks like it's fitting better to the data. And say, well, let's consider the case we use much higher degree polynomial, say 20. And we do the same thing as above, and this is what we get. We didn't set the seed, so each person might get different curve for this one at this time, but you get the idea. This is too wiggly for fitting this data. So this 20 degree fit seems to be an overfitting. And as we see the mean of coefficients, it really looks like so. We have very high coefficients, somewhat unreasonably high for 20 degree polynomial. We can easily see that the mean of coefficients are growing with the degree. And this is for plotting log scale for log plot for degree and average coefficients. So degree is in log scale and average coefficients is in log scale. We are putting blue circles and dotted line for this figure, and the marker size is 8 points. And even in log scale, this seems to be a huge jump. So what do we do in this case? What we do is using a model with some kind of regularization, which enforces simpler model to be created. Actually, this form of overfitting is pretty common with linear regressions. And linear regression we have used so far takes, in terms of optimization, takes this form. So we are finding the beta that minimizes this function, thus the squared error or quadratic error. So function of beta of data minus our target squared. And to avoid uncontrolled increase in our model parameters, we can penalize the large coefficients like this. By doing this, we are avoiding high numbers in model parameters, because if you have high beta, we have this term to decrease the beta. This addition of the second term is called regularization. And with this addition, we have introduced a hyperparameter alpha that controls the weight of regularization. And using this kind of regularization is called rich regression. So, and there is a class rich for this kind of model. So we import the rich model like this. And let's fit the 20-degree polynomial with rich regression. For example, let's put alpha to 1.0 in this case and predict the result. And the curve is missing the data a lot. And this is often the result of using alpha that is too large. So the resulting model is too simple. Let's try a similar value of alpha, say 0.001. And it looks to fitting the data better. And if we had very low value of alpha, we will get to overfitting eventually. And when we put 0 here, this is exactly the same as non-regularized model. So we get the undesired results, actually. So using the L2 norm squared is called rich using the rich penalty. And another popular method of regularization is by using the Lasso penalty, which is adding the sum of absolute values of all the beta. This is called L1 norm. And by doing this, we encourage sparsity in beta. So some of the beta j's will be exactly 0. And this works as some kind of feature selection that we mentioned on day 1. Let's have a break for now. And after the break, let's get to this in-class exercise, fitting a Lasso penalty to our polynomial regression example. Before going to break, is there any questions so far? All right, we return to 26. We are back from the break, and during the break, Julian put a nice question to the chat. Comparing this to yesterday's workshop, is optimizing C and gamma for support vector machine analogous to hierarchical regularization for this linear regression classifier? And my answer is yes, indeed. So many models will have different hyperparameters for the specification of the model, and the process of yesterday, it directly applies to fitting those hyperparameters. So you can split the data set into trained, validation, test set, like what we did yesterday. Let's split that into learning set and test set, and then we can use the cross-validation procedure on the learning set to choose the best value of alpha. And doing so will be left as an exercise for today's workshop. We will get to that later in today's session. Before that, let's discuss another part. Nitika asks, do you only choose linear regression if your data is a normally distributed error structure? Linear regression often assumes normally distributed error structure, and it works well in that case. But you can still use it when the error is not normally distributed, and there are similar regression model for the cases where the error structure is different from the normal. It depends on your situation again, and if you do some more statistical stuff like testing if beta is 0 or not, in that case having a normally distributed error structure might be critical for your statistical tests, and in those cases you will have to use a method that is like not much related to distribution. This circles back to what model to choose, which feature to use, right? Like the discussion yesterday. Yeah. Thank you for a nice question. So here's another model we discussed about regression, which is lasso regression, which uses this lasso penalty. By using our norm, we increase sparsity of beta. So what we will do right now is let's try lasso penalty for our polynomial regression example. So I just gave a word lasso right now. So what is the natural thing to do next? Yes, perhaps the first thing to do is checking if we have lasso in scikit-learn. So you can find lasso here. And yes, we do have lasso under linear model subpackage. So let's import this. Then what we do next? Perhaps next thing we do will be reading through the documentation and which keyword should we use for creating this. And in this case, we will use this parameter named alpha again. So let's put alpha equals 1.0 here. Then next steps will be fitting the model. And you will expect the same format of input as which regression we did before. So we will put that. And now we have created the model. Then we will visualize the fitted curve, just like what we did before. And what do we see? Just an intercept term, maybe. And it looks like everything became 0 for coefficients. Let's check that part. Yes, everything got to 0. So this is underfitting. The model became too simple. So let's change the value of alpha, say 0.1. It became slightly better. We got a linear model, but still it is too simple. Just the force coefficient is non-zero. So we will decrease alpha again, 0.01. It became better. We have 3 non-zero values up in here. Might seem still too simple, so we can decrease it a little bit and fitting better and better. And with very low value of alpha, we are getting a warning that says convergence warning, objective did not converge. You might want to increase the number of iterations. Why is this? Is that because our features vary a lot with the polynomials. The range of values differ a lot and distribution differ a lot. So the numerical convergence is not working well, really. So for Lasso, what is recommended to do is normalizing the features to have mean 0 and standard deviation of 1. This is done with the function normalize in scikit-learn preprocessing. That is when the different variables have no specific correlation between them, but in this case, because this is doing the normalization directly might be somewhat tricky. But in general case, it is recommended to use normalization. And what we can also do is combining the two regularization terms, this error norm term and this squares term, and we use both. That is named elastic net, and this is also widely used form of regression. So far, we have been dealing with the classification and regression, and both of them, we use label for training to map the features into those labels. And this hour, we will do just a little bit about unsupervised learning. There is no labels in the dataset, and we want to discover some hidden patterns inside the data to generate some descriptive statistics. So we have the dataset, and we will run some unsupervised learning algorithm, and we will get the result, which can be clusters, which is grouping of the data, grouping of the samples, and it might be new features, which describes the data better, and others. One of the most important unsupervised learning technique would be clustering, which is grouping example into certain group with similar features. And one of the most widely used method is k-means clustering, which is finding k clusters of points in which each observation belongs to a single cluster with the nearest cluster centers, and the cluster centers will be serving as a prototype of the cluster. And another type of clustering is hierarchical clustering. It seeks to build a hierarchy of the clusters. So from the 6 samples, we choose the 2 closest samples and group them together. In this case, B and C. And then we choose another pair of samples that are closest. In this case, D and E. And then we have 4 clusters: A, B and C, D and E, and F. And then we might add F here because if D and F are the closest, and then we can merge these two if these two are closest. And then if A is, and then lastly, to group all of them together, we can put this. And then to get the desired number of clusters, we can cut it at some point of this hierarchy to get desired number of clusters. Let's go to k-means clustering. This method partitions the feature space into k clusters based on the mean of points. Here is the algorithm. At first, we randomly initialize cluster centers. Say, from the 2-dimensional feature space, say that we randomly choose this red point, this green point, and this blue point as a cluster center. Then, at the view of each point, we can get the distance from this point, and we can determine which cluster center is closest from this point. And we do that to get the first iteration of clustering. We have this 1 point in red, and these 6 points closest to green, and these 5 points closest to blue. And with the new assignment, we can update the cluster centers. We have a single sample in this red cluster. So center of this red cluster is this point. So this red center moves here, and we can compute the average coordinate of these 6 points, and it moves here, and we get the center of these 5 points, it moves here. What we do next is going back to assigning the samples to the nearest cluster center. So these 3 becomes red now, and these 4 becomes green now, and the blue remains the same. This is repeated until convergence, when no more change in cluster happens. Let's explore the iris dataset using the k-means clustering algorithm. We first import the data using scikit-learn.datasets. So here is the iris dataset, which is among the most famous datasets in machine learning, and it is sometimes considered hello world example of data analysis. It has measures from 3 different species of iris plant: Iris setusa, Iris versicolor, and Iris virginica. And we have 4 features in this dataset: sepal length, sepal width, petal length, and petal width. To load the iris dataset, we import load iris function from the dataset sub package of scikit-learn, and let's load the data. It is 150 by 4 matrix, 150 samples, and 4 features. And we get feature names like this. So the first one is sepal length, second one sepal width, third one petal length, and fourth one petal width. So before we move on, let's visualize the dataset a little bit. You can change the, say, let's plot petal width versus sepal width in this case. So on the y-axis is the petal width, and on the x-axis will be the sepal width. So it looks like there are 2 huge groupings in here. And let's add some more details like this. Let's plot it as circles, and in this color and this marker size. And let's put X label, sepal width, and Y label, petal width. And then fit it to the frame. Now let's create k-means model and apply this to the iris dataset. Because we know that there are 3 different species of plants in this dataset, let's make an educated guess and use k equals 3. To do so, we will import the k-means class first inside the cluster subpackage. And among the hyperparameters in k-means, we have number of clusters, and clusters equals 3. And we will fit it to get the result of k-means clustering. After the k-means method is applied to the dataset, we can get the idea of the clusters to which each of the samples is predicted to belong by using the method predict. So with this, we get the cluster each data point belongs to. So the first person, so the first sample is in class 0, second in class 0, and these group into class 1, and these in cluster 1, and these groups into cluster 2. Let's visualize it by color coding each cluster ID. This is very similar to how we color coded different classes in classification datasets. So we will get the logical indices indicating which cluster each sample belongs to. Because we got clusters here, we get logical indexes like this. So for example, index 0 will have values of trues and falses, because most of the earlier samples are 0. We got true in the earlier samples. So we will put this class 0 to blue, class 1 to K. Which color was it? Anybody on chat? Yes, it was black. And for class index 2, it is red. So we get the points in these area blue, these area black, and these area red. And that is how clustering works. And let's try k equals 4 and inspect what comes out differently. We will do the same thing as before, except for that we put n clusters 4. And for this, we have the new set of index for clusters 3, and we will put it in green. And then we have the green cluster on the middle around here. Blue is intact and red is still here, black is still here, but some of them change it into green in the center. Because k-means assumes no number of clusters, there is some freedom, and k can be treated as a hyperparameter. And there are methodologies that do not assume the number of clusters to be known. Yes, I'll go through this first, and there are some methodologies that do not assume the number of clusters to be known. For example, density-based clustering, they don't need the number of clusters to be there, and it will just gather the nearby points based on how many points are there inside a certain area around some center. K-means is one of the simplest clustering algorithm, and it might not be ideal for your application. However, some modifications are still widely used. For example, K-medians, which uses median points instead of centers, and K-means plus, which which defines a initialization for k-means clustering. Because we start with random initialization, we might get the different results each time. So k-means plus plus is to get better initialization, capturing the better structures of the clustering at the first hand for initialization. And when applying clustering, what you have to remember is that this is different from classification, and if what you need is predicting categories associated to the samples, and if you have the labels, it is certainly better to use those labels and do supervised learning. If you don't, you can still get to this clustering method. And Nitika asked a nice question in chat. What if we know a few points have been misclassified? In this case, it is misclustered. Can we also do accuracy checks or penalizations in supervised learning? Yes, you can. Yes, you can do that. We can add penalties to certain objective functions of the clustering to get something sparse or something simple. For example, one of the examples I'm working on around this k-means clustering is putting only some of the feature centers to be non-zero and all others to be zero. So that we use only the important features for clustering. And about accuracy checks, we have measures for that. There is a measure named, what was it? Rand index, I think. Because we don't have labels, we cannot directly compute the accuracy. But one of the ways is that for each pair of the data, if they are in the same cluster in the true labels, and our clustering result, and if they are in the different subsets in X and they're different in our clustering result, and something like that. So in this case, A is number of pairs of elements in S that are in the same subset in X, and there are same subset in Y. That is counted for both numerator and denominator. And pairs of elements in S that are in different subsets in X and in different subsets in Y. This is also correct. This is also a sign of correct clustering. So we put it on the numerator. And C, the number of pairs of elements in S that are in the same subset in X and in different subsets in Y. This is the sign of incorrect clustering. So we do not put it in numerator. And D is the opposite way. So this is also the sign of incorrect clustering. So we do not put it in the numerator. So we get this kind of value named Rand index between 0 and 1. This would be one example of checking the similarity of clustering results. There also is a way to do some type of cross validation for clustering also, but that is not that simple, and we will not deal with that in this workshop. And also another question from Nitika. Do the clusterings also change if you run them repeatedly over time? In particular, particularly in k-means, it heavily depends on where the centers are initialized. So and the objective function is not convex, so we will go to local minimum, which means we get different results from each initialization. So how important are enough iterations? Oh, over time, you mean? To um if you iterate over and over, you what you do in this k-means clustering is that there is a function you want to minimize, and you are decreasing the objective function each time. So if you run this procedure too few times, you will get some underfitted results, which is not adequate. But as the iteration progresses, you will certainly get better results, but you might want to stop iteration because it takes too much time, or you are already there, so that the objective function value is no longer decreasing, or the cluster is no longer changing. And so if you have different clustering output with subsequent iterations, take the latest one. That is what I will say. And if you have run the clustering different many times with different initializations, take the one with the best objective function, because that will be the best result. Any more questions regarding clustering? The last item we will discuss is principal component analysis. You might have heard about PCA under different from different point of views. But yeah, PCA can be included in the umbrella of unsupervised machine learning methods. What PCA does is finding a new set of features that are uncorrelated among themselves. This is important and interesting because correlated features overlap in what information content they include. So we are looking for the directions that includes the most information we can get for each direction. The features are a linear combination of original features that maximally describes the variations in the feature space, and each of the features are perpendicular to each other. So let's talk a little bit more about PCA. There is a covariance matrix, which is a measure of joint variability of two random variables. It is defined this way. expected value of xy minus expected value of x times expected value of y. If the two variables are independent, then the covariance between them is 0. So for example, number of people, and if covariance is high, the two variables vary together. So if x is high, y is also high. So for example, number of people riding New York subway and probability of raining in New York will have high positive covariance because if it is raining, more people will be riding subway in New York. And covariance matrix is the matrix of covariances between each pair of variables in a set, which is always positive, definite, and symmetric. And what PCA does is changing the basis of this covariance matrix in the direction of that is describing the most variation. And after the change of basis, the covariance matrix will be diagonal, and the new bases are orthogonal from each other or uncorrelated. So from the original data set, we have the direction that is maximally describing this variation is this direction. So we choose this direction as the first principal component. And what we do next is, among the directions that is perpendicular to this, we find the direction that maximally describes the variation. And because it is 2D space, we only have this direction left. So we take this as the second principal component. And the PCA transformation means to get the coordinate based on this new basis. So let's work with PCA now. PCA is under decomposition subpackage of scikit-learn because this is a type of decomposition of the covariance matrix. To be exact, it is called spectral decomposition. And let's randomly generate 200 by 3 matrix, each of them between 0 and 1. And just for illustration purpose, let's put the last feature exactly the same as the first feature, so they are perfectly correlated. Then let's try to visualize the covariance matrix. Covariance matrix is under NumPy. And why did I put this x-axis here? Let's figure out. What happens if I just put x in here? We were thinking about 3 features, but this shape is not 3 by 3. 200 by 200. So this covariance matrix function is treating this data as 200 feature and 3 samples. Let's check the documentation of it to confirm that. We press Shift Tab, and we have it Let's see parameters. It says the argument M, the first argument, is array like 1D or 2D array containing multiple variables, rules, and observations. It says each row of M represents a variable, and each column of a single observation of all those variables. So we often have the matrix of the shape of number of samples by number of features, but this covariance matrix function expects it the other way, the transposition of it. So let's give it its transposition. If you recall, there was an attribute of this matrix, capital T, which returns the transpose. And now we get 3 by 3 matrix as we want. And let's visualize it. We are using matShow function of matplotlib, and we get this. So yellow means higher value, and this dark blue means very low value. Because the first feature and last feature, feature 0 and feature 2, are exactly correlated. So these of diagonal terms are very high. And the diagonal values are variances, so they are expected to be high. They are just variance. It's just variance of each variable, each feature. And by design, the first feature 0 and feature 1 has low correlation, so it is expected to have low value. Now let's apply this PCA transformation, initializing the PCA instance and fitting it. Then what we have an attribute of this PCA result is explained variance ratio, which means how much of the variation is explained by each principal component. First principal component explains 66.5% of the variation. And the second principal component, 3.3 times 10 to the negative 1. And because the first and third features are perfectly correlated, it is expected to have very low values for the third principal component. Let's see the principal component loadings. So each of the columns is the principal component. They are automatically normalized to have to have norm of 1. On the leftmost column, column 0 is the principal component with highest variance explained by it, and you can see very high absolute values for variables 0 and 2. And the second principal component mostly includes the variable 1. And the third component is the remaining direction that is perpendicular to both this one and this one. And you can apply transformation based on the PCA results. using the function named transform, using the method named transform under the PCA class. And let's see the results. Let's see the covariance matrix like this. You are getting very different values. From what I am getting, yes, there is nowhere because the random number being generated is different each time. But the explanation I did up to this point will still stand because of the construction we did. So after the PCA transformation, the transformed covariance matrix is expected to be diagonal. So we have almost zero off diagonal values and almost zero value in the variance of the last principal component, because it doesn't have much information content, and the first two diagonal elements are very high. Any questions so far? We will take a break now for 10 minutes and we will return 3:24. After that, we will have the very last hour of our workshop, which might end a little bit earlier. We will do an exercise of PCA and then go to the exercise notebook and some wrap-up comments. So let's go through an example of using PCA on a real-world data, which is breast cancer data we used on day 1. So we will load the data and split the data into training and test set. We will fit the PCA and let's visualize the importance of each principal component now. So we plot PCA.explained variance ratio underscore. Number of explained variance ratio entries, number of principal components is equal to the number of features we use, but in terms of explained variance, first 2 or 3 principal components explains most of the variation within the dataset. A better way to visualize this decay is using log scale, of course. So we put this line to make y scale in log. And then this is what we see. A common usage of principal component analysis is a way of dimensionality reduction. It is okay to choose only the first 2 of the principal components because explained variance ratio of the first two ratio is already well over 98%. And then all the remaining principal components together explains less than 2%. So we can choose only the first two principal components, and we can apply any other machine learning methods that we learned in this workshop on the data with the reduced dimension. So let's visualize the data set in terms of the transformed PCs. And we get this plot. The first dimension describing most of the variation, and here is the second principal component. And we can fit a random forest classifier, for example, on this transformed two-dimensional features, like this. We import random forest classifier with 100 trees and maximum depth of 5. And we take first two columns of the PCA feature matrix and then fit the model. And use the same transform to put the test data on onto the space of principal components, and then run prediction and compute the scores. And we are still getting an okay result with only two features. One thing that is important to note is that even when we are doing dimensionality reduction or any kind of normalization or transformation, we should only use the training data to make the transformation. So to do the transformation here, fitting the transformation for PCA, we only use the training set here. So test data does not influence the learning process, any kind of learning process. We just look at the test data at the very last moment. So we are still getting an okay result with only two features. And on a very high dimensional data set, such as gene expression, where the number of features is much higher than the number of samples, this kind of feature selection often improves the results. That is the main contents, and let's go to exercises. We have a exercise notebook for day 3, and if you are taking this workshop for UCLA credits, you need to submit this notebook and the one for yesterday. So about this as your homework until next Thursday midnight to my email. And please submit both that IPYMB file and the HTML file converted from this notebook. And here are the tasks. Exercise 3 is hyperparameter tuning for penalized regression. So consider the data and rich regression algorithm and lasso regression with the 20-degree polynomials as in the class. And we will tune the parameter alpha using k-fold cross-validation based on the R-square coefficient of determination measure. And the steps will be similar to what we did with classifiers. So what you are to do is load the data file regression exercise dataset, which is used for our in-class examples, using which function? It was numpy.load.txt. And we will split out the test data and choose the best hyperparameter alpha for which regression using 4-4 cross-validation. And the score method of the which class and Lasso class will give you the coefficient of determination. And then you will choose a hyperparameter alpha for Lasso regression using the 4-4 cross-validation. And you will compare the final performance of the two with the test set. And then the second exercise for today will be principal component analysis and k-means clustering. So let's try PCA on the iris dataset. You will compute covariance matrix, fit the PCA, and then you visualize how much of the variance is explained by each principal component, and what are the principal components. And you will perform the PCA transformation, and you will try to visualize what is the covariance matrix on the transformed space. And you will plot the samples on the first two principal components, and you will exercise some of the visualization schemes, like using different colors and markers for different kind of iris. And you will perform k-means clustering with k equals 2 on the PCA transform space, and you will visualize the results using the first two principal components. By the way, this exercise and yesterday's exercise, what you were asked was using this k-fold instance to get the indices and run the score, get the scores for each fold. But if you look at the documentation of scikit-learn deeper, and then you might find some shortcuts to save some time for your homeworks, maybe that is not disallowed for the homeworks. Now let's get to the concluding remarks. We extensively explored Jupyter Notebook and Jupyter Lab. We explored useful functionalities from NumPy and matplotlib libraries, NumPy for numerical arrays and matplotlib for plotting. And we studied supervised learning and its two fundamental subfields, namely classification and regression. And we investigated scikit-learn structure and discussed in detail how to use its documentation pages. And at the end, we briefly discussed unsupervised learning. So this figure is for classification, getting the decision boundary between the classes. That is what this figure is showing. And this is a plot for regression, and this is for clustering. One prominent topic we did not cover in this workshop is neural networks. And due to recent advancements in hardware using multiple layers of neural networks have been massively successful in many fields, including image classification and segmentation. I believe it deserves a separate workshop with higher hardware demand, including access to GPUs. And there are some hand-related books that you might find helpful regarding machine learning. First book is Hands-on Machine Learning with Scikit-learn, Keras, and TensorFlow. This is perhaps taking a similar approach to this workshop, and it will give you some information in deep learning with Keras and TensorFlow with its recent updates. And second book is Pattern Recognition and Machine Learning by Christopher Bishop. It gives you some mathematical approach to machine learning. Another book is An Introduction to Statistical Learning by James Witten, Hasty, and Tipshirani. This is a intro-level book for people with a little bit of knowledge in math and statistics. This is written by statisticians, so it will be in R, and it is not that heavy, considering how heavy these people can get. And one of the most recent books released is Machine Learning, a probabilistic approach by Kevin Murphy. This is more mathematically advanced and puts more emphasis on Bayesian statistics. And it comes with some online software, which is in MATLAB. And there is a nice introduction book for deep learning written by the fathers of deep learning, Ian Goodfellow, Yoshua Bengio, and Aaron Colville. So the goal of the workshop was to provide basic information to become independent and increase the knowledge with online resources. I hope this workshop helped you in this direction. And there are some links I have to provide you. The first one is quiz. They are multiple choice questions, and you will have to complete this quiz if you are taking this workshop for UCLA credits. And there is a workshop evaluation survey, which Elo introduced at the beginning of today's workshop. It will be, so your input will be appreciated for improving our workshop, improving our collaboratories workshop program. So that is it. Thank you for attending this workshop. And if you want to stay around and do your exercises, you can stay here and ask any questions coming up. And if you want to leave now, you can do so now. Thank you very much for attending.